Alright, how's it going everybody? I am here recording this video on Thursday, April 22nd. Today we're going to talk about section 4.2, sinusoidal forcing. In the previous video, we looked at our first look at some forcing terms being included in our second order differential equations, our harmonic oscillators, and we're looking to see now how we can handle various types of functions being applying forces to our objects over time rather than us just sort of releasing our systems to go as they're going to go. We saw that our general solutions to forced harmonic oscillators are always going to include a homogeneous solution plus a particular solution, where the homogeneous solution is the components that go to zero when plugged into the left side of the differential equation. The particular solution are the terms that turn into the forcing function when plugged into the differential equation out there. We've seen that finding the two of them is two totally separate processes. The homogeneous solution relatively easy. It's what we did in section 3.6 last chapter. The particular solution is the stuff that's a little bit more special to the forcing function that we're currently looking at. So I'm gonna do my I want to say real quick here, I just made this entire video and then my computer froze with about 1 minute left to go in the video, and I lost the video because it did not get to like complete it, and so it's a corrupted file. So I feel like I just said literally all this stuff, so I'm gonna do my best to still remember to say everything, but I think that I'm going to, I don't know, I feel like I just said this, and in the effort to not repeat myself, I'm going to try to not repeat myself, but that video doesn't exist, and so it's not a repetition. So hopefully I still remember to say everything and don't feel like I'm just doing infinite repeats here. So in the last section, we looked at these three examples that you're looking at right here, and we made some guesses for the particular solutions that are associated with them. And so remember what happened in these ones. In this first one right here, we guessed that our particular solution was going to be e to the negative t. It didn't work. That's when we said, listen, maybe we should guess up to constant multiples. So then we guessed that our particular solution should be k e to the negative t. We found that our k was going to be 1/2, and so that gave us our x sub p being 1/2 e to the negative t as our solution. In the second example that we did, we learned our lesson from the first example, and we guessed that our particular solution should be k e to the negative 2t. But then we found that this didn't work, and it didn't work because we ended up with an equation that led us to like 0 equals 1. So that says to us there is no value of k such that this is a good particular solution. Then we remember what we learned back in section 3.5 about our repeated eigenvalue scenario, and we said sometimes when you think you should be getting exponential stuff, it's actually exponential stuff times t. So we just sort of made a guess that we are going to get something like that here. And when we did this, we found that this did work with just a simple k being equal to 1. And so that told us that our particular solution should be t e to the negative 2t. Finally, then, we looked at a third case here where rather than having an exponential function, we had just a constant function over here. And so our first inclination maybe would have been to guess that our particular solution should just be a. But we said, well, from the last one that we learned that sometimes you want to multiply terms by t, so maybe there should be a bt term in there as well. So we guessed the much more robust solution, a plus bt, because we didn't know which components we actually needed in there. What we did is we found that b was unnecessary, meaning that we found that b was equal to 0, and we got a being equal to 4/3, and so that just gave us our particular solution, just being straight up 4/3. And you should notice that the reason why this works over here is because if you take the derivative of this x sub p right here, the first derivative is 0, the second derivative is 0 since it's a constant. If you plug in 4/3 into just x, 6 times 4/3 does in fact give you 8. So we can see that that particular solution does actually work out in this case right there. So hopefully what you're aware of, based on the title of this section, is that today we're going to let our forcing functions be sinusoidal functions. It'll still be the case that we can very easily find our homogeneous components of our solutions, but we'll need to make smarter guesses to get our particular solutions. So we're going to actually kind of do some more real math with this one here today. And in general, I like to think that these sinusoidal forcing functions are really the way that I more naturally think about this, right? Because when we talked about this, like the mass on a spring scenario, it's like we like pull the mass on a spring back and we let it go, and we just let it go. And our solution for x of t just described the motion of that mass on the spring over time, which we saw would always like go to rest. because we always had some form of damping being involved there, right? I think that it makes the most sense to think about our as applying a force for it to be sinusoidal. Not like it makes the most sense, but in most of the scenarios that I imagine it, that's what I'm seeing there. So I'm picturing things more like pushing my child on a swing is what I'm picturing there, rather than just pulling the swing back and letting go and letting him go forward, back till he comes to rest at the bottom. I'm instead thinking pull back, letting go, but then me, every time he comes back, I'm applying a periodic force to the system to perhaps keep it in motion rather than allowing it to just decay down to no motion and being at rest at the bottom down there. So that's kind of like what I picture when I picture that we are adding a periodic or sinusoidal force to a system. I like to think about just like pushing a kid on a swing, right? So, so let's go ahead and just kind of take a look at an example here, kind of get right into it, see what parts are going to be easy for us, see what parts are going to be hard for us. And what I'm thinking right away is that the first hard part for us is you guys needing to remember how do we deal with the homogeneous type information that we're going to get out from this. So what we remember from our previous video is that when we look for our homogeneous solutions, x sub h is it's the solution that is associated with the homogeneous equation, meaning the equation where we are actually just equal to 0 over here. The thing that makes this easy is that when we're equal to 0, this is completely equivalent to a linear system, which we know from our eigenanalysis is going to allow us to jump straight to our characteristic polynomial of lambda squared plus 2 lambda plus 2 equals 0. I can see that I can't factor this, so I'm going to go to the quadratic formula, negative 2 plus or minus the square root of b squared minus 4 times a times c, all over 2. It seems to me like this is going to give me a 4 minus 8, which is negative 4. So I'm going to get a 2i where the square root is over 2. And that's going to lead me to my eigenvalues of negative 1 plus or minus I that's associated with this guy here. So what I want to now do is write my homogeneous solution associated with these eigenvalues right here. We want to remember that when we found these solutions associated with complex eigenvalues, we said that they were going to be like our e to the lambda t, but in our case here, our lambda is our negative 1 plus I times t, which we could write as e to the negative t times e to the it, which we could write as e to the negative t times cosine t plus I sine t. Then we said the real component will be its own solution, the imaginary component will be its own solution, and therefore we can take linear combinations of the a term and the b term here to get the general solution associated with this homogeneous equation here. And that led us to our leads us to our homogeneous solution for the for our forcing equation right here of being k1 e to the negative t cosine t plus k2 e to the negative t sine t. All right, so here is the general solution to this second order differential equation, which is not the thing that we're actually overall interested in. What I know is that these are the components that are going to go to 0 in the long run, and I can see that from the e to the negative t components. As t gets bigger and bigger and bigger, this goes to 0 over time. If I plug this equation into the left side of this differential equation, I'm going to get 0. That's literally where it came from. What we now need to do is we now need to find the particular solution for x that's going to allow this left-hand side of the equation to become sine of t, right? So we've got sort of half of our solution to this forced harmonic oscillator here, but we've definitely got sort of the easier half of the solution. So now what we want to do is we want to guess the form of the particular solution x sub p, right? And what we know is that we're doing this with our forcing function f of t being sine of t. So just like in the last section, the last video, we obviously want to guess functions that we think that when we take their 0th, first, and second derivatives and constant multiples of them and combine them, we're going to get back sine of t. So we want to guess something that's going to result in us getting out sine of t. So it seems very reasonable that our very first guess that we should be making here would be that our particular solution should be something like a times the sine of t. All right, that seems like a reasonable and upfront guess. But here's what's going to happen. If we guess our particular solution to be something like sine of t, then up here what we're going to get is that this is just going to be 2 times sine of t. This is going to be 2 times cosine of t. And that's kind of a problem because this is then going to be negative sine of t, the second derivative of sine of t. I don't have any buddies to cancel away this cosine term that we're going to get, because there's no cosine on the right, but we're only going to get one of it on the left, so I don't have it anywhere for it to go. So if I just pick sine of t to be my guess for my particular solution, or some constant multiple of it, some cosines are going to get introduced, and they're not going to have buddies to like cancel away with, since I need to arrive at just sine of t is the total final amount out there. So those cosines wouldn't have anywhere to go. So then you could say, well, hey, listen, then maybe we should just beef up our guess a little bit right here and include some cosines. And that's not the worst idea ever. But if we make guesses like these, what's going to end up happening is we're going to run into an algebraic mess, because we're going to have 4 total parameters then floating around in our system, because we got our K1s and our K2s as well. And that's going to lead us to some things that are just going to be very difficult for us to end up managing out here. And so we want to make a kind of a smarter version of a guess right here. So here's the deal. We currently have a sine function, but I feel like making my guesses associated with sine functions is hard, because sine functions introduce cosine functions. And so it's really like there's this whole other function that we need to manage that's not even any component of what we think that we should be ending up with for our forcing function. So my question to you is, back in chapter 3, where did we learn that we can get sine and cosine components from? Right? I want a component of sine, and I am wondering if there is any way that I could generate a sine function from a different style of function. And I'm looking at it right here, right? Where I know that I've seen my sines and cosines being managed in chapter 3 was really from complex from complex exponentials, right? So here is what we're going to do. Back in chapter 3, we learned that sine and cosine components come from the real and imaginary components of e to the it, or in this case, that's e to the 1it, because we just have sine of 1t, right? So what we're going to do is a process called complexification. What we're going to say to ourselves is, listen, dealing with trig function gets a little bit hairy, because you bring in one trig function in derivatives, and all of a sudden you've got 2 trig functions. We've now got 4 parameters to manage. Don't really want to do that. So instead, what we're going to do is this. We are going to rewrite our differential equation that has a sine of t in it. We're going to replace that sine of t with e to the it, and I know that that's a kind of reasonable thing to do, because I know that this is just cosine of t plus I sine of t. And so it looks like we want to keep the imaginary component of whatever we find. So you should notice now that this is now an imaginary valued equation. So we should expect to get imaginary valued solutions, but we only want to keep the imaginary component of that complex number, because we started with sine, and sine is what's tied to the complex component of the e to the it stuff over here. If this was a cosine over here, then we would complexify, we'd find an imaginary solution, and then we'd only keep the real parts, because cosine is tied to the real component of our imaginary exponentials, right? So that's kind of what I'm saying in this paragraph here. Since our forcing term is sine of t, which we know to be associated with the imaginary component of e to the it, we're only going to want to keep the imaginary component of the solution that we end up finding here. And so to kind of justify this a little bit right here, I just want to say, and what I'm actually going to do is I'm going to change this to be, I'm going to write this as x sub c as our complex solution here, which is going to have a real and imaginary component. Because our forcing function is tied to the imaginary component of complex exponentials, we're going to keep the complex component of our final x sub c. If that was a cosine, we'd keep the real component of x sub c. And so what I'm saying here is that x sub c of t is going to have a real component plus I times an imaginary component. And so with our second order differential equation here, our complexified differential equation over here, we could recognize this to be the second derivative of our real plus our imaginary plus 2 times the derivative of our real plus our imaginary component plus 2 times our real plus our imaginary component should be equal to, and what are we equal to over here? Well, this should be our cosine of t plus I sine of t. All right, so if I expand this a little bit, we're just getting x double prime r plus I x double prime I plus 2x prime r plus 2x prime sub I, that's I times 2x prime I, plus 2x sub r plus, oop, there's an I right there as well, plus 2ix sub I should be equal to cosine of t plus I sine of t. And so now we're going to do the thing that we always do, which is whenever we have an imaginary number being equal to an imaginary number, we've got a plus bi equals a plus bi. We want the real parts to be equal, and we want the complex parts to be equal. So it looks like what I can go ahead and do to rewrite this is to say the real parts grouped together. So I'm going to get my real part, my 2x prime real plus 2x real, plus my imaginary parts, I times the imaginary parts, which is going to be x sub I double prime plus 2x sub I prime plus 2x sub I, should be equal to our cosine plus I sine. And then we can write this as our two equations, right? We've got our a plus bi equals c plus di, means that a equals, let me just write this, a plus bi equals c plus di implies that a equals c and b equals d, right? So I'm just setting my real parts equal to my real parts and my imaginary parts equal to my imaginary parts. All right, so this says, this is our scenario right here. Because we have a sine of t as our forcing function, we'll only want the imaginary component of x sub c. Right? Because our forcing function is just a sine function, you can see that's tied to the imaginary component of a complex solution that we're going to arrive at here. So now our forcing term looks like the exponentials that we saw in the last section. That's really good. Let me go scroll back up. Now that we've complexified our forcing function is an exponential function, and we saw that it was really, really easy for us to make our guesses associated with our particular solution and to find the appropriate particular solution, right? But since our guessed particular solution will include real components that we don't want, let's call it our complex solution. And then when we're done finding it, let's just say, oh, and we, by the way, we only wanted the imaginary parts, since the imaginary parts are all that we started with, the sine parts, that's tied to the imaginary stuff right here, all right? So let's go ahead and do that here. So we're going to guess our x sub c. So we had that our forcing function is now e to the it. So we're going to guess that our x sub c should be a e to the it. In that case, our derivative of x sub c should be I a e to the it. And our second derivative is going to pop down another I, so that just makes it a negative a e to the it. And we can go ahead and we can throw all this stuff into our differential equation. When I do this now, I'm getting negative a e to the it plus 2 times I a e to the it plus 2 times a e to the it equals e to the it. I'm going to go ahead and divide this whole dang thing by e to the it, since that's not doing much for me right now. It's in every single term. And our goal is to know what value of a makes this work out. So I'm solving for a here. So it looks like I have a negative 1 and a positive 1 right there. So it looks like a plus 2ai equals 1. And a times 1 plus 2i equals 1. And it looks like a equals 1 over 1 plus 2i. So this is good. We found our version of a that we want. But remember, we don't want to keep all of x sub c. We only want to keep the real component of x sub c. So what my issue is going to be now is that I can't separate the real and imaginary components in this form. So we need to rewrite this in a slightly different form here. Can't separate real and imaginary components. in this format. So let's multiply this a by a conjugate here. So I'm going to multiply by 1 minus 2i over 1 minus 2i. That's going to clearly give me a 1 minus 2i on top. On bottom, I'm going to get 1 squared plus 2 squared, and that's because positive 2i times negative 2i is negative 4i squared. Negative 4i squared is positive 4. And so that's going to give me 1 minus 2i over 5, and that's going to give me 1/5 minus 2/5 I, right? So this is maybe a better version of A for me, because this is something where I can separate out my real and imaginary components, and I know I'm going to need to do that. Remember, we sort of backed out to get more than what we wanted for our complex solution so that we could do our math easily with exponentials. Then once we find our solution, we want to pick out only the slice of the terms that were actually related to our original problem, which in our case will be the imaginary components. So now that we've found A, well, so let's kind of say what we did. So we guessed x sub c equals a e to the it. We found a equals 1/5 minus 2/5 I. We only want the complex component, or the imaginary component. So let's go ahead and do this stuff here. So now we can go ahead and say, so let's take this stuff here and say our x sub c was a e to the it, which we now know that we could write as a, which is 1/5 minus 2/5 I, times e to the it, which we know as cosine of t plus I sine of t. And I can go ahead and multiply this out, and I can then find my real versus imaginary components. And I want to write my particular solution so bad, I'm still one line away. So I'm going to get 1/5 cosine of t plus 1/5 I sine of t minus 2/5 I cosine t plus 2/5 sine t. And notice importantly that this negative 2/5 I times positive I sine t gave me a positive 2/5 sine t, because I times I was I squared, to give me -1 to cancel with that negative there. Now I can see that my x sub c really looks like my 1/5 cosine t plus 2/5 sine t. That's my real part, plus I times 1/5 sine t minus 2/5 cosine t. And there's my imaginary part right there. So this is what we want. So I think that we're getting x sub p is our imaginary component of x sub c, which is 1/5 times the sine of t minus 2/5 times the cosine of t. And so now that we have our x sub p, we had also seen that we had x sub h was our, what was it, e to the negative t cosine t. Oh, wait, there's some k's in there, isn't there? I think it was all just coefficients of 1, though, right? I think we got a k1 e to the negative t cosine t plus k2 e to the negative t sine t. And now that we have our particular and our homogeneous solutions, we can add those two guys together. And you can see down here our general solution is just our homogeneous solution there that we got from our eigenvalues. And here is our particular solution that we got from complexifying, because we like exponentials for making guesses. We then applied the exponential to determine the coefficient on the exponential that was going to work. We re-expanded our guess so that we could get our real components versus our imaginary components. And in this case, the reason that we kept only the imaginary components was because our forcing function only involved the imaginary component of its complex version right here, right? The sine is tied to the imaginary parts. Again, if this was cosine t right here, we would have done everything the same, And the only thing that would be different if our forcing function was cosine is we would have kept these components here instead of these components. That's the only difference right there. So this math is the same whether it's sine or cosine. We're just choosing to pick out the parts that are actually related to the problem that we were originally given right there. So we can find our general solution to be the sum of the homogeneous plus the particular. And the question is, what should our long-term behavior look like? Remember in the last video, we already kind of talked about this. We said it should be the case that for any forced oscillator, for any oscillator in general, sorry, the word I was looking for was damped. For any damped oscillator, we are always going to get negatives on our exponentials, meaning as time goes off to infinity, this whole x sub h expression is going to go to 0 because we have negative exponentials, right? So what should be the case is that as time gets larger and larger and larger, this stuff is going to 0. As time gets larger and larger and larger, that stuff's just doing its oscillating, right? So what I'm thinking is for small times, so near the origin, we're going to get some action from these first terms. But in the long run, our solution should basically just look like that particular solution there. This, by definition, is the stuff that's going to 0. That's like literally how we defined it. So let's go ahead and take a look at that in Desmos here and see that we are, in fact, going to get that type of behavior here. So there we go. So there we go. Thank you for not freezing on me this time. That's important. So what you can see that I've graphed right here is this entire general solution. There's our homogeneous components. There's our particular components. I've got A and B as our K1 and K2. And importantly here, this is just the particular solution. I'm claiming that our general solution is just going to look like the particular component of it in the long run right here. And you can see exactly that happening in our graph. This blue graph here is the overall solution, and what happens is at the beginning it's doing whatever it wants, but then later on it comes to just agree with that black curve, just our particular solution. And it doesn't matter what kind of wonky coefficients we give this thing. Sometimes it might take longer to end up agreeing with that particular solution only, but eventually this thing just matches this thing perfectly in the long run because these leading two terms right here have gone to 0 as the x component or t component gets larger right there. So this does match my intuition that we should have just ended up doing some sinusoidal stuff eventually, but that we could have done some weirder stuff at first. But these terms only have like non-zero value at early. Later on, they're essentially 0, e to a negative power out there, right? So this graph sort of confirms what we were suspicious was going to happen out there. We're just agreeing with a trig function eventually, right? So very cool. So it turns out there's still some additional adjustment that we want to make to this solution right here. This is one of those things where I totally understand that this is a slightly better version of giving an answer. I am not 100% convinced that the effort that it takes to do this is worth the additional value in how our final solution looks. But I can tell you that our book does do this for every problem, and that My Open Math, I'm pretty sure, does do this for like every problem as well. So there is one last adjustment we want to make just to how this looks. So all that's coming up right now is just some trig stuff right here, not necessarily some calculus stuff. But basically the bottom line is what we would like to do is we would like to re-express our particular component of our solution as a single trig function, which hopefully is believable for you based on what we're seeing. Oh, that wasn't the move right there. Based on the fact that this, to me, come on, just looks like a trig function to me, right? This doesn't look like anything too crazy right there. It seems to me like there should be one trig function that I should be able to write that would describe that curve that's out there. So we're going to do a quick little trig manipulation here, and our goal is to rewrite this group of terms as one single trig function here. So here is how we're going to go ahead and do that. And I typed all this out because we'll write one out though as an example. So here's what we're going to do. So just follow along with me right here. This is one of those things where I do expect you to know what I'm doing as I say it. I don't necessarily expect you to just generically remember it for the next time you go to do it. I do expect you to be able to look this back up when it's time for you to make this process happen. So here's what happened. We guessed the complex component, or sorry, we wanted to find our particular component of our overall solution. So we complexified, that's why I'm calling it x sub c, and we made our guess that we were going to get a e to the it. We did some math, and we found that our a should be 1/5 minus 2/5 I. But what I know is that since a is an imaginary number, a also has a polar form that involves exponentials with base e. And that's important because the other thing that a is multiplying is an exponential base e. So maybe those can combine nicely. So what I'm going to do is find the polar form of the complex number a. So to find polar form, I need my radius and I need my angle, right? To find the distance that we are from the origin, we just take the square root of the sum of the squares, and you can do your little bit of arithmetic right there, and you'll find that we're going to get a 1 over root 5 as our distance that this point is from the origin. The other thing that you can do is you can go ahead and you can look at the angle that this makes at the origin. You can see that in the complex plane, we go 1/5 of a unit to the right, and we go 2 units down. So we certainly should be pointing downward at like something like a 60-degree angle, something like that. We're going to find that this is approximately a negative 63-degree angle is what this makes relative to the positive x-axis. So it seems like what we can do is we can rewrite this a that we found. We found a to be this 1/5 minus 2/5 I, but we just figured out that we can rewrite it in polar as 1 over root 5 e to the negative 63i, where that 63 is measured in degrees. Way more typical to do this in radians, by the way. I don't know. I did this one in degrees. So what we can do is we can now rewrite that guessed particular solution x sub c. The guess was a e to the it, but we now have a better expression for a that's in polar form, and polar form of an imaginary plays nicely with these exponentials here. So it looks like this is an exponential base e, this is an exponential base e that's multiplying it, so we can add their powers up here, negative 63i and it, and they both have a component of I. There's a positive t and there's a negative 63. So now by writing it in this form right here, we now can use Euler's formula to expand into the cosine plus I sine, where the what's inside of the cosine and sine is the constant, or is the multiple of I in the exponential. And finally, we only wanted the complex component because we were interested in that forcing function being the sine of t, which we associated with the complex component of Euler's formula here. And so therefore, I'm only going to keep the sine, or the complex component of this, which happens to also always be the sine function for the exact same reason, because it also came from Euler's formula. And finally, for some reason, it's standard to always write this as a cosine function. I don't know why that's the case, but we can just use our quick little trig identity that says sines and cosines only differ from one another by an additional rotation of 90 degrees. So that says to me we should be getting this cosine of t minus 153, 90 degrees off from 63, to be our cosine version of that particular guess right there. And so this is our way now that we have now combined that sum of sines and cosines into being a single cosine function right here. So here's what I'm going to say. Again, technically, you should recognize all the math that I did here, but I doubt anybody's like, oh yeah, I can do that in easy, no problem. I doubt that that's where we're at. I do expect that looking at this, you can say, okay, I've technically seen all that before, I can do this. And I do expect you to be ever so slightly skeptical. So I feel like it's a completely reasonable thing that we go and look at a graph and confirm that these are in fact the same. My claim that I am making to you right now is that this difference right there, the difference of that sine and cosine, is exactly equal to this single cosine expression right here. And over in our Desmos graph, I have graphed both of them. And so we can take a peek at both of them over here. And what you can see is here is our particular solution in terms of both terms. Here's our particular solution in terms of a single cosine. Notice real quickly, we had 153 degrees. Desmos likes to think in radians by default, so I multiplied it by pi over 180. That's the only difference you're seeing. But what you can see here is these graphs are clearly laying exactly right on top of each other. They are the same graph right there. So this is our good way to convert a sum or difference of trig functions into a single trig function right there, is by way of Euler's formula right there, which is a little tricky and roundabout. But again, like I said, I don't know why it's so standard to do this, but it does seem to be the case that our textbook and My Open Math will keep on doing things like saying, find the general solution to this forced harmonic oscillator. State your solution of the form blank plus blank plus blank, where the third blank is just a cosine function or something like that. And so you have to be in this form if you're going to submit your answer right there. So a little bit hairy with a little bit of bonus trig right here, but definitely something that you can do a little bit of converting an imaginary number into polar, multiplying two exponentials together, using Euler's formula to re-express in terms of sines and cosines, only keeping the component that we were originally interested in, because originally we had a sine function, so we kept the imaginary part, and then converting it to cosine right there. Right? So that was a little bit hairy, but now what we should do is we should do one nice big example here where we actually like lay out all of our process. So in this one here, we're going to like give our step-by-step process. Our last thing is going to be to convert our particular solution into that of a cosine function. So this is our like slightly improved method of giving our final answer here now. So by the way, I guess before I should scroll away, I should say, so now we can actually write our x of t as our k1 e to the negative t cosine t plus k2 e to the negative t sine of t plus 1 over root 5 cosine of t minus 153 degrees right there. So this is our alternate way of writing our general solution. And it makes the analysis just a little bit simpler now because, again, what we know is what's going to happen here is that this homogeneous solution is going to go to 0. It's much, much easier for me to discuss what happens in the long run when my long run function is just one function instead of a sum or difference of two functions. So I think that's that perceived additional benefit that we get right there. So let's do another example, and what we're going to importantly do in this example that's going to be ever so slightly different is, one, you can see that we've got a cosine function as our forcing function, so that means we're going to be interested in keeping our real components rather than our imaginary components when we do all of our complexification. The other thing that's going to be really important that we're going to do here at the end, which is what crashed my computer about 35 minutes ago, is that I want to graph this thing and I want to see what this looks like importantly in phase space. Notice that in Desmos and in all the math that we've been doing here, we've been given equations that are only, sorry, I'm scrolling a lot here. We've been given equations that are only in terms of x and t, and therefore we've been finding solutions that are only in terms of x and t, right? But what we know is that our phase space involves a whole second variable, what we've been typically calling v for velocity, the derivative of x. We could totally go and look at that right now. We're going to see a cooler version in the next one coming up right here. So recognize that we're only hanging out in x land. There's not a system here. However, we can convert any second order differential equation into a system, which means we can get our phase plane diagram of this guy by converting it to a system and throwing it into our Python graph out there. And we're going to see some real satisfying result come out of this. Also notice in this guy, we've got an initial condition. So that says our position and our velocity at time 0 is going to be 0. And so let's go ahead and find our homogeneous solution, find our complex, make a complex guess, keep only the real component because we're in cosine. So that's going to help us find our particular solution. That'll help us form our general solution statement. We can then apply our initial conditions to solve for K1 and K2, and we'll have our final solution out there. We will try and interpret our final solution before we look at the graph to anticipate what kind of graphs we should see. Then we'll go and graph it, and we'll feel some very deep satisfaction about the graph that we're looking at out there. I promise. These are super sweet graphs that we're going to see here. So let's do the things in order here. Step 1, I got to find my homogeneous solution. So what that means to me is I only want to look at my homogeneous differential equation here. So that's going to be x double prime plus 2x prime plus 10 just equal to 0. That's going to allow me to write lambda squared plus 2 lambda plus 10 is equal to 0. And I can see that I can't factor this thing, so I'm going to have to go to my quadratic formula here and get a lambda equals negative 2 plus or minus square root b squared minus 4 times a times c all over 2. I can see that underneath the square root, I'm getting 4 minus 40, which is negative 36. The square root of that should give us 6i. So negative 2 plus or minus 6i all over 2 is giving me negative 1 plus or minus 3i. I can directly go from this lambda right here to writing my general solution. It's easy when we're not in the vector form. The vector form is where you guys got to go find eigenvectors and all that stuff. I think that's the hardest part of those system solutions here. But since we're only hanging out in X land here, pretty easy for me to just directly write my homogeneous solution when we get these eigenvalues of negative 1 plus or minus 3i right here. I should just be getting k1 e to the negative 1 is telling me what's up with my real components. That's my negative t for my power here. That 3i is my complex component. That's going to be the arguments inside of my sines and cosines here. So it looks like this is my good homogeneous component of my overall solution right there. I still need to find my particular solution. I still need to apply my initial conditions, but we found our first chunk of our solution. So my next step now, since I want to head towards finding our particular as opposed to our homogeneous component of our solution, is I'm going to complexify this since I see that we've got trig functions on the other side. So I'm going to go ahead and rewrite this now as x double prime plus 2x prime plus 10x equals, and it looks like in this case I want to write this as 4e to the 2it. That 2 is the 2 that we're seeing inside right here. Looks like that coefficient of 4 is just coming along for the ride. Now that I see that this is actually what I'm going to write my forcing function as, my complex forcing function as, I can guess my complex solution associated with that right here. And it seems to me like my good guess for x of c is just going to be some a e to the 2it. You know, well, I don't know what we're going to get. That 4 is clearly like hanging out there, but I'm thinking some constant multiple of e to the 2it is what I would want to guess x to be to get more terms of e to the 2it out there. All right, so that's going to be my guess. We need to know what components we're going to want right here. I know that my e to the 2it is really my cosine of 2t plus I sine of 2t. And we clearly started this problem with a cosine of 2t being what we actually had before we complexified and introduced new terms. That means to me it's the real component is the components that we want to keep. So because we had f of t equals cosine of 2t, or I should say it was, you know, proportional to that right there. I don't care about that 4. That's not affecting me at all. We will keep the real components. Another way I might say this is that the particular solution that we're on the hunt for is the real component of the x sub c solution that we're actually guessing, right? So we're going to find x sub c based on our method of undetermined coefficients. So I want to find a. Then I'm going to find the real and imaginary parts and just discard the imaginary parts because we didn't have those terms in our original differential equation, right? So let's go ahead and apply our guessed x sub c to our equation now. So what I'm going to see here is we guessed x sub c was going to be a e to the 2it. I know that I want to plug this thing into our second order differential equation. Sorry, our complexified. I was going to write cosine right there. I need to write my e's. So that means I need to find my first and second derivatives of this guy. So x prime is going to be 2ia e to the 2it. Our x double prime of c is going to be, another 2i is going to come down. It's going to give me negative 4ia e to the 2it because that negative 4 is from I times I, which as I say it makes me realize that that I should not be there. So now I can go ahead and plug these guys in right here. I'm getting negative 4a e to the 2it for x double prime plus 2 times 2ia e to the 2it for x prime plus 10 times a e to the 2it for x, and that should be equal to 4e to the 2it. I'm immediately recognizing there's an e to the 2it in every single term, so I'm just going to divide that away, and I should be left with negative 4a plus 4ia plus 10a equals 4. It looks to me like that's 6a plus 4ia equals 4, or 3a plus 2ia equals 2. I'm trying to solve for a. 3 plus 2i equals 2. And so I can go ahead and do my division, but we learned a lesson last time. Is that this is not quite a good format for us. We're going to need to be able to separate our real and imaginary parts. So I'm going to go ahead and multiply by the conjugate on top and bottom so that I can separate out my real parts from my imaginary parts. Up on top, I'm going to get a 6 minus 4i. On bottom, I'm going to get a 9 plus 4. And that's going to give me 6/13 minus 4/13 I. Right? Just doing my little bit of arithmetic there for a. So now we have found, so that was our method of undetermined coefficients. We guessed that this x guess would be good for our exponential forcing term. We found the coefficient of a that makes it a good guess. But because we introduced some new terms by complexifying, we now want to get rid of the terms that we didn't actually care about. So now what I want to do is I want to find x sub p, right? And what we said was that this is just going to be the real components of x sub c. So let's multiply out what x sub c is and find just its real parts, right? So x sub p is equal to the real part of x sub c. And we had that x sub c was a e to the 2it, which we just found we should be writing as 6/13 minus 4/13 I times cosine of 2t plus I sine 2t. And we want to multiply this out, and we want to keep only the real components because we started with a cosine expression. So it looks like here I can see we're going to get a 6/13 cosine 2t. We're going to get a plus I times 6/13 sine of 2t. We're going to get a minus 4/13 I cosine of 2t. And we're going to get a plus 4/13 sine of 2t. Notice that this is a plus because positive I times negative I is negative I squared, which is positive 1. Right? So now this is our x sub c right here. It looks like our real part of x sub c. So x sub p is our real part of x sub c. I'm just going to keep those two real components, which is 6/13 cosine of 2t plus 4/13 sine of 2t. So this is sort of like we did it. We definitely have our homogeneous part, and we have our particular part. We can add them together and we're done. We should just be mathematically responsible and convert this guy into the cosine statement like we had previously seen. So we want to rewrite A in polar to make this happen. So we had that A was 6/13 minus 4/13 I. So we can find that the magnitude of A is the square root of the sum of the squares of those two terms. I can see that I'm going to get in the numerator up here, I'm going to get 36 plus 16, which is 52. In the denominator down here, I'm getting 13 squared, and we're taking the square root of 13 squared, so I'm just going to get 13. And it turns out that 52 is actually 4 times 13, so I'm going to be able to write this as 2 root 13 over 13, or just 2 over root 13 if you want right there. I'm fine with that. The other thing we need to find is theta, which is going to be our tangent inverse of our b value over our a value. It's like our vertical component divided by our horizontal component there. So that should be negative 4/13 divided by 6/13. And if you go throw that guy into your calculator, you're going to find that to be about negative 33.69 degrees right there. So we've got our magnitude, we've got our angle. So it seems now like we can write A, which was written in standard form as 6/13 minus 4/13 I. I can now instead write this as 2 root 13 over 13 e to the negative 33.69 I, not theta, that one, I just wrote theta. Now we can multiply out that x sub c that we had right there, or excuse me, our x sub p. I guess that was our x sub c, the a e to the 2it, right? Yeah. So we got a e to the 2it, and that is now going to be 2 root 13 over 13 e to the negative 33.69 I, that's a, times e to the 2it. Well, I can then just write this as 2 root 13 over 13 times e, and it looks like I had two t's here and negative 33.69 here, and that's all the I stuff that I had. And so now I can write this as one, I can use Euler's formula to now expand this. And what we know is we only want the real component. And so it looks like we're actually going to end up getting here that our x sub p is going to be 2 root 13 over 13 times the cosine of 2t minus 33.69. I don't need to convert that into anything else because it's already in cosine. So that should be giving us our general solution. So it's going to be our homogeneous plus our particular. Our homogeneous solution was the k1 e to the negative t cosine 3t plus k2 e to the negative t sine 3t. And now we get plus our particular solution, 2 root 13 over 13 cosine of 2t minus 33.69 right there. So we found our general solution. All right, so a bunch of work right there, but we managed to do it. We kind of did our nice methodical step-by-step process right there. So this is saying we're sort of, remember, I think about this as like stepping back. So we're including more stuff than we should have included, but it makes it easier to do our math in complex land. We did the math in complex land, and then we're like, okay, let's go back to real land now. But then we got to say, wait a minute, which parts of all these things do we want to keep? And you should say, well, where did we start from? And you should say to yourself, well, I start with cosine, which is the real component of Euler's formula. So I'm only going to keep the real parts of the solution that I found, or vice versa with the sine and the imaginary parts that are out there, right? So here's our general solution that we found. Now, as our final thing that we want to look at today, stop underlining things in red that aren't wrong. Word, what's wrong with you? The final part of the day, what does this look like out there in phase space? And here's the thing that you should recall here. Remember that as time goes off to infinity, our homogeneous component should be going to 0 because it experiences the e to the negative t. This component should be what survives in the long run right here. So it seems like our long run position expression is just our particular component right here. So this stuff right here is only for the long-term solution, right? The long-term position function should just look like this x of t. And then if we wanted to find our velocity so that we could plot this in phase space, then it seems like this should just be the derivative, right? So the derivative of cosine is just negative sine, and then times the derivative of the inside function is going to pop out an additional factor of 2, and we can see it right there. Instead of a 2, we got a 4, right? So my question to you is, what is this the parameterization of? And you should know the answer to that question. You should recognize this to be the parameterization of an ellipse. We've got our x and y, our cosine and sine, but the difference is one of them has a coefficient that's twice what the other is. So what I can see here is that my v components, my velocity components, the stuff that's going to get graphed on the vertical axis here, it looks like it has an amplitude that's twice as large as the amplitude for the x stuff. So I think that I'm going to get an ellipse that's twice as tall as it is wide in the long run in phase space. That's not just what our trajectories look like. That's what it looks like once we've gone out far enough in time that we've let our homogeneous components go to 0, right? So again, I'm expecting this stuff to do kind of whatever it wants at the beginning when there's still some meaningful contribution coming in from the homogeneous solutions. But in the long run, it's going to tend towards the particular solutions. In the long run, it should tend towards being an ellipse in phase space that is more vertical than it is horizontal. So if we want to go and plot this thing in Python, what we know that we need to do is we need to convert this thing into a system. And in fact, if you're going to do this in over at Bluffton, you also need to convert this into a system. It doesn't take in those second order differential equations there, right? So we had x double prime plus 2x prime plus 10x was equal to 4 cosine of 2t. I know that I'm going to want to talk about my x double prime component in 1 second here, so I'm just going to do this immediately for myself. And so now I'm going to convert to a system. I know that the way that we convert to a system is the same always. The derivative of position is velocity. the derivative of velocity is acceleration, and that's sitting right there. So it should be negative 2v minus 10x plus 4 cosine of 2t. Now, before I pop over to Python, you should notice one really, really important thing. Every single thing that we've thrown into Python did not have a t in it. Our phase plane grapher is only currently stated for autonomous differential equations. However, it's really easy to make the adjustments necessary. There's no thinking whatsoever to make the adjustments necessary to make our grapher work for this system as well. And so I've already made those. So let's go ahead and take a look at what we've got going on over here. Hey, hooray. Right here is where my video froze last time. So I got all the way to here making this video last time. All I'm trying to do is just show you a graph and call it a day right here. And so I'm so happy to now be to the new component of this. All right, so I did update our grapher ever so slightly. So let's go ahead and take a look. And what I think I might as well do is restart and clear all output here just so that we know that we're all fresh. So I'm going to do the standards, import the 2 required libraries. I decided that for this one, this gets really, really hairy to look at a whole bunch of a whole bunch of initial conditions all at once. So I'm just going to start with the initial condition that we said that we were going to do for this problem, which is just the initial condition of 0, 0. So that's the only one I'm leaving active. And the important thing is here, we've seen a whole bunch of different things. We've seen our linear systems here, where we define A, B, C, and D, and do AX plus BY, CX plus DY. We looked at the van der Pol equations in 5.1. We looked at the non-polynomial example in 5.1. But today we want to look at our sinusoidal forcing example. So what you should see is that this, in terms of F and G, is now exactly what we had just come up with one moment ago, is that we said that our dx dt equals V, and dv dt equals negative 10x. And by the way, did I get that the right ordering right there? That is negative 10x minus 2y plus 4 cosine of 2t, plus 4 cosine of 2t. So I've got all that in here. But the important adjustment that I had to make to all of these functions is that we have been writing these just as like f of xy. I needed to include that t is possibly an input as well, because we literally see that happening over here. It looks like I need to know x and, I'm sorry, where's my cursor? I need to know x and y and t to compute dv dt. So those have to be all 3 of the arguments required for that function right there. So I just expanded all of these to include that t component right here, because I don't want things to be like mismatching when I go to try and do other things. But what that means is, and if you're looking to update yours, you just need to go ahead and throw in a t comma in front of every single usage of f and in front of g that occurs out here. Those all occur, only just, there's the 4 f's right there, the 4 g's there, 4 f's there, 4 g's there. Those are the only 16 total places that we use f and g in this thing, and they're all like kind of nicely in rows right there. So you just got to, put your t commas up here and put your t commas down here. Everything was already built to track that information. We just didn't use that as an argument in any of our functions yet. So again, we're only going to plot one solution curve with the initial condition of 0, 0. And I needed to update my formulas to take in a time as well as a position for x and for y, or what we're thinking of as velocity here. So I'm going to run this cell, run it. I don't think anything else has really meaningfully changed here. And I'm going to keep on plotting these things here. And oh, how satisfying is this graph right here? You should be saying, oh, hell yeah, right now. So here's what happened. Starting at 0, 0, as promised, this thing did sort of whatever it wanted. It was doing not necessarily ellipse stuff. And by the way, just ignore the dashed line completely. We're thinking forwards time right now. So from the initial condition at 0, 0, it was doing things that weren't representative of an ellipse. But as time went on, our trajectory became more and more associated with only the particular solution. And the particular solution for position, as well as its derivative, we had previously discussed, should be forming an ellipse that's twice as tall as it is wide. And I'm seeing that exactly right here. So just as a smidge more satisfaction associated with this one, let's go ahead and just check out some other like initial conditions out here. I don't know. Let's start at 2, 0. So starting out to the right of where that ellipse actually should be. So the ellipse is here, and we're going to start off to the side of it out here rather than in the middle of it. And let's go ahead and rerun everything and see what we look like. And once again, starting here at 2, 0, we took some big old swoop, but eventually we're being brought to hang out over at this ellipse that's twice as tall as it is wide, because this is what our particular solution insists is what our behavior is going to look like in the long run. In the short run, the homogeneous solution is having an effect on our trajectory. In the long run, the homogeneous solution has no effect, and it's just that one particular solution component that's dictating that sort of ellipse type behavior that we're seeing out here. So this is pretty cool that we can kind of see things tending towards a stable orbit of an ellipse in the long run, which I think is kind of a little bit more interesting behavior than we have seen in the past from a lot of these guys. So I kind of just want to bring in um, some of these pictures right here, and that's all I've got for you guys here now. Um, I just want to throw some extra graphs in here, and I'm going to go ahead and call it a day. So that wraps up our sinusoidal forcing here. You can see that we use some slightly fancier techniques for sinusoidal forcing than we did for exponential or constant or linear forcing that we're going to see out there. But this idea of complexification and taking serious advantage of our understanding of Euler's formula and trigonometry kind of helped us get to some clean results here by thinking in terms of imaginary numbers. And I think that you guys should start taking the lesson away from imaginary numbers that is really what sort of the adult mathematicians think of, which is that imaginary numbers in one sense kind of make things a little bit more complicated because it now requires two components to talk about one number. But what they do is they give you more room to move around, right? And that's exactly what we did here. We said we feel a little bit restricted if we just had to stick with sines and cosines. But when we go into exponential land, we now get to use exponentials. Or sorry, when we go into complex land, we get to use exponentials to represent our sines and cosines. Those are much, much easier functions to work with. So our math became easier by introducing the complex numbers. We just had to do the steps of bring ourselves into complex land and bring ourselves back out of complex land so that we could enjoy the benefits that exist in complex land. So this is a general truth about most things in math, which is that the word complex is like the opposite of what it does. Complex numbers often make things work out easier for us. It's giving us a whole other dimension to move around in, to do our math in, and that often makes the math end up being easier. So every time complex numbers get brought in, it's because we're making math easier with them. Always, and we saw that happen here today. So that wraps up sinusoidal forcing for me today. You guys can see that our remaining topic of the semester, just as we hit 2 sections of chapter 4 today, hit a section of chapter 5 last week, we're hitting 2 sections of chapter 6 next week for our Laplace transforms. That is going to be kind of a whole different animal than everything we've seen this semester. I would go so far as to say it might be the most hardcore calculus that we do of the entire semester is next week, but it's going to be a really cool way that we're going to use calculus to convert calculus problems into algebra problems. So similar to how complex numbers gave us more space to move around in today to make our math easier, Laplace transforms are going to philosophically follow that same approach where they're going to transition us into a new space where the math gets easier. So our effort is going to be get into the new space is hard. Doing the math is easy in that new space. Getting back out of that new space is also going to be the challenge right there. But the math is going to be easy once we can figure out what this new place is that we want to do math in. So I will see you guys next week for our Laplace transforms. Have a good one, everybody.